just put that when you can in this area. Put it in a pocket or a belt or anything like that.
Okay.
Thank you.
So you ready to go?
Yeah, I'm just contemplating my Blackboard strategy.
I know, it's challenging.
I
figured out.
Yeah. Okay. All right. I think I'll do this, and then
That's probably a good idea. Start with those down. So you have that gives you more to use.
Well, I just want. I mean, this is a lot of overhang. So when I put that up, I'll bring this one down.
Yes. Okay. So we have marked it on top. We got Entanglement Entropy 1.
Right. Okay. So as far as I understand it, my job is to watch Juan's lectures and then explain them to you. So, I was actually a student in TASI '99, so I haven't been back since. But it was a lot of fun, and I still know a lot of people from that. So, all right. So I'm talking about entanglement, and there are a bunch of reasons that you might be interested in entanglement. Maybe you want to build a quantum computer, or maybe you want to characterize ground states of various Hamiltonians or condensed matter systems, or maybe you want to, I don't know, pad your H index. For me, the biggest reason that I'm interested in this is that I'm interested in quantum gravity. And so of course, this has been a major challenge in theoretical physics in the last several decades. So I think we've certainly made a lot of progress. And through string theory, I think the state of the art in understanding quantum gravity is this ADS-CFT correspondence. Okay, and you. Yes, I could write lower. Okay. Okay. There we go. Okay, so this is a really big thing in understanding quantum gravity because it really gives us an example. So it gives us, we think, or some of us think, a non-perturbative description of certain quantum gravity theories for spacetimes with particular asymptotic behavior. Okay, and the main example would be asymptotically ADS spacetimes. And so one thing that I'm going to, so asymptotically ADS spacetimes. So these are spacetimes which, as you go out towards the asymptotic region, they're maximally symmetric, negatively curved spacetimes. And there's actually some choice about what, so they have a boundary in a certain technical sense, even though it's an infinite distance. It takes light rays a finite time to get out there. And there's a certain boundary geometry that in a sense you get to choose. So when we talk about asymptotically ADS spacetimes, you have to specify what boundary geometry you're talking about, and that could be Minkowski space or a sphere times time or various other options. Okay, so yes. And so this correspondence says that these particular theories are exactly described, or that a precise description of such a theory is in terms of some non-gravitational system. And usually that's some quantum field theory. In this ADS case, it's a conformal field theory. There's some simple examples where it's just a ordinary quantum mechanical system. But we'll focus on the ADS and the CFT case. And so for that example here, this would be some conformal field theory on this same fixed geometry that, that we have as our boundary over here. Okay, and so So what does this mean? Okay, so starting with your field theory on that space, then you can have lots of different states. You could have the vacuum state. Okay, and then that would correspond to some empty ADS space with that boundary. So pure ADS. In these lectures, the main examples that I'll be thinking about are where this is Minkowski space, or sometimes it'll be a sphere, or possibly hyperbolic space. But you can do other things. But then if you consider other states, so say add some energy on this side. Okay. Well, that might correspond to now a geometry that is asymptotically the same, but is different in the middle. So maybe you've added a gravity wave in the middle of the space-time, if you've added a little bit of energy here. Or if you add a lot of energy here. Okay. For example, if you consider a thermal state with high energy, then that can correspond to something which is much different than your original empty space-time, such as a black hole. Okay, so that's the basic thing that we'll use. There's all these different states over here. And at least some of those states have some kind of classical geometrical description. And the different states correspond to different geometries. Yeah? I'm going to talk about that later. Yeah. Okay, so that ADS-CFT correspondence has been around now for getting close to 20 years, and we've got all kinds of evidence for it. But I think it's still not proven, and I think there's still some gap in our understanding of why it works. There's still some really big questions about ADS-CFT. And so in general, we could ask how, why, when do space-time and gravity emerge from the physics of some non-gravitational system, some CFT that usually has lots of degrees of freedom and it's usually strongly coupled. Why is it that you have something in that description that's equivalent to some space-time geometry? Why is there gravitational physics somehow? How exactly is that encoded? Also, even in examples where we believe in the ADS-CFT correspondence, it's still not totally clear exactly which states of the CFT are ones that have a dual that corresponds to some nice classical geometry. Maybe other states correspond to more quantum things like superpositions of different geometries. So there's a bunch of really basic questions that we'd like to understand. And so the connection with entanglement is that recent work has indicated that entanglement, physics of entanglement in this field theory, may play a crucial role in understanding some of these things. Okay, so specifically, it seems that the entanglement structure of this quantum field theory state, which is something that not too many people thinking about field theory cared about until recently, and then recently, I think maybe first in condensed matter, and then gradually in our community, people started thinking about this more. So it seems like this entanglement structure has some direct connection to the dual space-time geometry and structure. And furthermore, various constraints that entanglement in field theories or in general quantum systems have to obey seem to be directly connected to some gravitational physics, or at least some constraints on the dynamics of spacetimes. Okay, so I think in today's lecture, I'm going to give you a fairly general picture. I might say a few things, again, that Juan said, although in different ways. Okay, and some things that he didn't say. So I wanted to start by mentioning that the first hints of this connection happened long ago. Okay, so the first hints of some connection between entanglement and geometry really came at a time when people weren't thinking too much about entanglement. So this work was the work on black holes and thermodynamics in the 70s. Okay, work of people like Bekenstein and Hawking. Okay. And so, for example, back then, people thinking about classical and semi-classical gravity realized that the area of black hole horizons seemed to have properties or obey properties very similar to entropy in statistical mechanics. Okay, so if one makes some analogy between horizon area, okay, over 4g Newton to make it dimensionless, and entropy, okay, well then you have analogs in gravitational physics of the laws of thermodynamics. Okay. So there's a first law where the mass of the space-time takes the place of energy, and this area takes the place of entropy. So you have something that okay. So this is like dE equals TdS. The thing that's playing the role of temperature is some constant associated with your black hole called surface gravity. And then something like a second law that says that classically these areas of black hole horizons can only increase in time. Okay. And actually, so it's an analogy. It's mysterious why these geometrical quantities should have any relation to thermodynamic quantities. Hawking's calculation showed that it was probably more than an analogy. So Hawking realized that, in fact, black holes actually have some temperature, and that, starting with that, I think people started to take more seriously that this area should actually be interpreted as a legitimate statistical mechanical entropy. Okay. But it wasn't until much later that that there was any understanding of what that entropy was counting. I guess it was within string theory. There was work by Strominger and Vafa in 96? Okay, I was going to say 95. 96, where they in some examples in string theory really understood some stat mech counting of states in a certain system that matched with an area of some black hole horizon. Okay, but I'm going to jump ahead actually to ADS-CFT. That I haven't said entanglement yet. Oh, okay. That is not an entanglement entropy calculation. Yeah, that one was counting some states. Yeah, but okay. I mean, right. I'll get back to that a little bit, but like if you wanted to, you could say it's the entanglement entropy with whatever heat bath is. I mean, formally. Yeah, I agree. Yeah. Okay. So in ADS-CFT, we can understand that provides us a context for this. So ADS-CFT, again, it's some theory where we actually know what we're talking about when we talk about, say, the Hilbert space of our theory of quantum gravity. We know what we're talking about. We know what states live there. We could talk about actual, counting states. And so in the ADS-CFT context, the reason why areas are obeying relations like entropies is that if we have a black hole on the gravity side, well, this is understood to be, so this is some large black hole in global anti-de Sitter space. This is understood to be dual, or the CFT description is that this is some thermal state of the CFT on a sphere. Okay, so this is the usual canonical ensemble where you have energy eigenstates appearing with probabilities given by the Boltzmann weights. Okay, and so then the statement is that in this correspondence, the area of the black hole is in fact the entropy, the thermodynamic entropy of the CFT, okay, which in terms of these probabilities is given by this formula. Okay, so this is just the standard formula for the entropy in terms of the probabilities that determine this canonical ensemble. Okay. Okay. So that's some connection between an entropy in the CFT and some aspect of geometry in the dual spacetime. So Ryo Takeyanagi, I think one mentioned that. You've probably heard about it. Ryo Takeyanagi can actually be understood in a simple way starting from here. Okay. So really what their observation amounts to is just saying that instead of considering the entropy of the entire CFT, okay, and saying, well, that thing is dual to some geometrical quantity, some area, it's also a well-defined thing to talk about a subsystem of the CFT. Okay, and as I'll review now, and Juan talked about it, but I'll review it again. There's an ensemble of states that one can associate with any subsystem of a quantum system, and there's an entropy that one can associate with such an ensemble. And Ryu and Takeyanagi observation or conjecture is just that that subsystem entropy also has a geometric interpretation. Okay. Okay, so entropy of subsystems and it has a geometric interpretation not just for, say, this thermal state, but for more general states. Or I should say for general states that would have some classical gravity dual. Okay. So so when I say Ryu Takeyanagi, I'm going to usually mean Hubini, Rangamani, Takeyanagi, which generalizes away from that. Yeah. So I'm going to review this statement later on, but for now I want to start by reviewing in a different way just this notion of entropy of subsystems, and I wanted to say a few things that Juan didn't mention. Okay, so some of the things Juan certainly said already, but it's probably useful to review. Okay. Okay, so I want to consider some general quantum system, which I'm going to denote by this ball. This used to be, say, a CFT on a sphere. Now it's a general quantum system. And this A is going to be some subsystem. Okay. And so I'll start with a slightly simplistic statement that the Hilbert space is a tensor product. Juan spent some time talking about the extent to which one can that's actually true in a field theory. But let me start by imagining that that's actually true, or we're doing some lattice regularization in the field theory so that it's true. Okay, so there's a basic thing in quantum mechanics, which is that if I'm interested in this subsystem, if I want to know properties of the subsystem, observables that I calculate related to that subsystem, so I might want to ask, well, what is the state of the subsystem? And you might think at first that there's going to be some vector in this Hilbert space for the subsystem A that captures what that subsystem is doing in the context of a general state of the whole system. Okay, and that turns out not to be true. Okay, so if I want to describe the state of okay, so it's not true in the sense that there's in general no vector in this Hilbert space such that any operator acting on that space, so what I would want would be to find a state A of the subsystem so that any operator living in that subsystem would have the same expectation value as it has in the entire state of the whole system. Okay, so the statement is that there's no state for a general choice psi for a state of the whole quantum system. I'm not going to be able to find a state of the subsystem such that this is true for all operators. Okay. Okay, so but you can still talk about the state of the subsystem. And let me write it up here. Okay. And the way to do it is to say that even though you can't choose a single state such that this is true, you can always choose an ensemble. Okay, so you can always represent the state of the subsystem by an ensemble of states of pure states. Okay. And that would be, what I mean by that is some set of probabilities and orthogonal states. Okay. Okay, and so if you've chosen this ensemble correctly, then what you will find is that for any operator O, living in the subsystem, the expectation value of that in the full state is going to agree with the expectation value computed in the ensemble, which means that you compute the expectation value in all of those orthogonal states and then just average them using the probabilities. Okay. Okay, so you should think of the state of the subsystem as being an ensemble of pure states. This ensemble is often referred to as a density matrix. So it's by some simple manipulation, we can notice that this is equal to trace of the operator A times a matrix rho, where rho is equal to this sum. Okay, so rho is this weighted sum of projection operators. These individual things are operators that project on those possible states. Okay, so this is the density matrix for the subsystem. Okay, so ensemble, density matrix. The other terminology that people would use to describe this situation would be a mixed state. Okay. And so, right. So all of these things are kind of the same concept. And so another way to say that is that not more than one of those probabilities is non-zero. Okay, so there's a special case where the ensemble only has one state with probability 1, and that's the case where the subsystem actually is in a pure state. The generic case, you're going to have a bunch of probabilities that sum to 1, but they're not going to be just 1, 0, 0, 0. Okay, and so the terminology, so entanglement is basically exactly the situation where this is true. So when you don't have a pure state of that subsystem, then we say that subsystem is entangled with the rest of the system. Okay, but that's really the same thing as this classical kind of notion that there's some classical uncertainty associated with the state. Okay, so A being entangled with the rest is the same as there exists some classical uncertainty about the state of A. Okay, and so given that, then it's very natural that we quantify this uncertainty in exactly the same way that we quantify the uncertainty here. Okay, so we can quantify that by entropy. And we use exactly the same formula. Okay, so it's exactly the same. It's not this entropy here is precisely the same thing that we're always talking about. We're just looking at a subsystem. We find that's generally going to be in an ensemble. If we were doing thermodynamics, we would say, okay, the entropy of that ensemble is given by this. Okay, because of this equivalence, people also refer to this entropy as entanglement entropy. Okay, so this is the same thing. As entanglement entropy. Sometimes in this quantum context, it's so you can write the formula as something expressed directly in terms of the density matrix like that. Yes, yeah, so I could have put an A, right. Any other questions? Yes.
My lack of knowledge, but once you're back working with density matrices and things like this, why do I have to carry the word entanglement around in my head? This is entropy, right? I'm doing funny kind of quantum statistical mechanics.
Yeah, I mean, I think it's it's just that we're applying this entropy formula to ensembles which are not the canonical ensemble and not the microcanonical ensemble. These are completely general quantum mechanical ensembles, and so in that sense, it's a little bit different. But
Of course, if I was scattering,
sure. So that's a good point. We could also, I talked about starting with a psi. We could actually have started with a density matrix for that larger system. But I think the terminology doesn't really change. People still, so of course, because you could of course, I'll get to this in a second. You could of course choose an even larger system where that system is a subsystem of the larger system, and then the larger system could be in a state psi, and then it would be, it would just be A would be a subsystem of this big system in a state psi. Okay, so far, right. So psi is, we've had, in general, psi is a pure state of the full system. And we've seen that given some subsystem A, you can define this density matrix, or equivalently this ensemble. And then you can compute this entropy. Okay, so expressed in terms of entanglement, this really quantifies how much is the one system entangled with the rest of the system. Okay, so when people talk about entanglement in an elementary way, they're often talking about states like this versus states like that. So not entangled. entangled. And so, but if I were to put coefficients here, and this one is really small, I would say this is less entangled than the case where alpha and beta are 1 over square root 2. And so this entanglement entropy would be a way to quantify that, to actually say that, yes, there's this quantitative measure that says this is less entangled than the maximally entangled state. Okay, so in a general quantum system where there's lots of possible subsystems, these entanglement entropies for all of the different subsystems represent quite a lot of possible information about your state. It doesn't tell you the entire state, but it tells you a lot of information. I'll just mention a couple of other things that people talk about in this context. So one thing that comes up, Juan may have mentioned it. Okay, so there's something called Renyi entropies. Okay, so these are basically derived from the trace of the nth power of the density matrix. Okay, and so you see that would give you the sum of these eigenprobabilities raised to the nth power. And sometimes people consider the case where alpha is not integer by analytic continuation. And one of the main reasons for doing that is that the limit as alpha goes to 1 of this Renyi entropy is the entanglement entropy. Okay. These Renyi entropies are often easier to calculate, but they're probably less natural in that they don't obey as many nice properties as entanglement entropy. And the other thing you'll hear about sometimes, okay, which is really the most general way of characterizing this ensemble or these probabilities, is just the whole spectrum of probabilities. So this is sometimes called the entanglement spectrum. Okay, and so knowing all of the Renyi entropies for all of the different integer powers would be equivalent to knowing this entanglement spectrum. Yep.
I heard entanglement spectrum is the eigenstates of molecular Hamiltonian.
Yeah, I'm going to talk about what the modular Hamiltonian is directly related to that density matrix. So it's just the log of the density matrix. And so if you know the eigenvalues of the modular Hamiltonian, that's also okay. Yeah, so that's equivalent to knowing that. It may be that the term, I'm not sure actually if the standard terminology is that entanglement spectrum is these guys or if it's the log of those guys, but it's the same information. Yeah. I don't think so. So generally, in fact, no. So generally, if I just know the density matrices for various subsystems, then I can't reconstruct the whole state. Often you can show that. So there may be special systems where you can. Often you can do it by counting. You just figure out how many parameters do you have to use to write down a general density matrix, or a set of density matrices, and how many parameters you need to describe a general state. And often the latter one is bigger. Okay. So we can also sometimes we can go in the other direction. Okay. So sometimes given an ensemble rho, you might, without a contact, so maybe someone says, here's a thermal ensemble. So sometimes it's interesting to go in the other direction and look for what's called a purification. Okay, so So that would be a pure state of a larger system where the subsystem is in this density matrix. And that's something where there would be an infinite number of possible ways to do that. Okay, so we can, given an ensemble row, we can find many purifications. Okay, and so generally, the answer to what one of these purifications looks like, starting with this ensemble. So I introduce some auxiliary quantum system. So we have our system A. I introduce some system B, which could be of any. Well, okay. So it generally can't be too small, but there are lots of options. Okay. So you introduce this auxiliary system, and then if you have a state that looks like this, okay, so it's a theorem that if you manage to find a state of some enlarged system such that the density matrix for the subsystem is this, that state can be represented in this way, okay, where you have a sum over these probabilities, and you have the square root of p, and then you have your states here of the first subsystem, and then those are tensored with some orthogonal states in the auxiliary system. Okay, and so it's easy to check. Starting from that, you can compute the density matrix for the subsystem A, or the ensemble for that subsystem, and you find it's equal to that one. But it's also possible to prove that for any pure state of the enlarged system, you can represent it in this way. Okay, so this is known as the Schmidt decomposition. Schmidt. Okay, and this is occasionally useful for proving things. So in particular, one thing that this implies is that if I have a pure state of the larger system, the entanglement or the spectrum of these probabilities for the subsystem A is the same as the spectrum for the complementary subsystem. So it implies that row A and row B have the same spectrum. So sometimes the other subsystem is larger, in which case it might have a bunch of additional zero eigenvalues. So when I'm talking about the spectrum, I'm just talking about the non-zero probabilities here. Okay, and because all the p's are the same, then you have the same entanglement entropy and Renyi entropies. Okay, so if I have a quantum system in a pure state, and I want to say what is the entanglement entropy of A, that's the same thing as the entanglement entropy of B. So that's measuring, in a sense, the entanglement between A and B. Okay, okay, and so an example. Oh, I've got that one. An example where we might, we often think about doing that would be when you have a thermal state. Okay, so there's some system at temperature T, and so the idea that this system at temperature T is really a system in contact with a much larger system. Is this same idea. So we can think of that as actually being a state coming from a heat bath coupled to our system. And there are many possible choices of what the heat bath is. It just generally has to be large enough. So So there we would say that the pure state of the system plus the bath gives you the thermal state. Okay, and then interestingly, so then the thermal entropy over here, if you want, you could say, oh, that's just measuring the entanglement between the subsystem and the bath. So the thermal entropy is equal to the entanglement entropy of the system with the bath. Yes. Okay.
What is quantum and what is classical?
So you could say that the whole thing is quantum. I mean, you can always say everything is quantum. What we usually think of as being classical when referring to the smaller subsystem, I think we usually think of these probabilities as being classical probabilities. Okay, because this is when we talk about the ensemble of these states, and I compute something in the ensemble, I just compute the expectation value for each state, and then I average those expectation values with these probabilities. There are no cross terms. Okay, so the classical part would be the fact that we say that there are these probabilities. This is the expectation value of the operator O in the ensemble. Okay. Well, in the sense in the sense that it's much different than if I were to have written this. Okay, so I could have written this object. And that would be a quantum superposition of all of those states. And then if I computed the expectation value of the operator in this state, I would have all of these terms, but then I would also have a whole bunch of cross terms. Okay. When we're talking about an ensemble, I simply compute the expectation value in each of the states separately, and then I average with the probability. So that's just like I said, okay, I'm going to roll a dice, and if it's this, I get this state, and if it's this, I get this state. So that's classical. Yeah. Yeah, I mean, so we usually, this is a different point. When talking about entropy, so everything that I've talked about so far is sort of some precisely defined thing. There's often this notion of coarse graining that one uses when talking about entropy. So that's I guess an additional element of classical physics that comes into discussions of entropy, but I won't really be saying anything about coarse-grained entropies. So, in this quantum stat mech presentation of entropy, you just calculate it using this formula in terms of the probabilities. And if you want to think of the entire thing as being a pure quantum state of the bath plus the system, then it's precisely the same thing to calculate this entanglement entropy. I mean, the other thing that we often, normally when you talk about the canonical ensemble, you assume that the interactions between the bath and the system are extremely weak. Okay, so that I can think about energy eigenstates of the system, and I don't have to worry about the fact that those are no longer energy eigenstates once I couple to the bath. Okay. So there's one kind of special example of a purification that I think Juan mentioned, and that comes up in these discussions quite a bit. So I'll just review that. Okay, so a special case of a purification starting with a thermal state is this state called the thermofield. Double. And that's where you take your auxiliary system to be the same as your original system. And so if we do that, okay, then the formula that I wrote over there reduces to this formula here, where the p's are equal to these Boltzmann weights again, and if I want, I could write that all out. Sorry. Like this. So where EIB is just the equivalent state to EIA. You have two equivalent systems. And so this is a quantum superposition of states where each subsystem is in the same pure state. Okay, that's stuck. Okay, so I'm going to go back to ADS-CFT, but if there are any questions about this general quantum mechanics stuff, now would be a good time. Yes?
Are you assuming that the Hilbert space is finite dimensional?
No, not. I mean, generally, I don't need to assume that it's finite dimensional. So if I have harmonic oscillators or something, it wouldn't be. So going to an infinite dimensional Hilbert space is not usually a big deal. When we get to talking about quantum field theory, then one needs to worry about UV issues. So I think Juan spent a fair bit of time talking about these things. But the summary of what happens going to field theory is that for certain quantities, like the straight up entanglement entropy of a subsystem of a quantum field theory, you find that this is UV divergent. However, there are plenty of sensible quantities that you can talk about that still capture the physics of the entanglement. So, for example, you can talk about mutual information, which is a measure of entanglement and correlations between two subsystems. So in this combination, divergences cancel. Or you can talk about S. You can talk about sort of differences of entanglement entropies for a region A for two different states. The difference in entanglement entropy is typically well defined. But yeah, I guess we'll get to some of these things later. Okay, so back to ADS-CFT. All right, so I want to do an example in ADS-CFT that brings in some of these ideas. So I said at the start of the lecture that the CFT and the thermal state, say on a sphere, is equal to the black hole. is dual to a large ADS black hole, and that the entropy, the thermal entropy of the CFT, is equal to the horizon area. Okay. So there's actually an interesting question, even when I just write this down. CFT and thermal state on SD is dual to a black hole. So I think Witten was the first person to point this out or suggest that. But an interesting question is that's become more and more relevant is, well, exactly what do you mean by the black hole? Exactly what information does this CFT have about the black hole space-time? Because we often talk about the black hole and say Schwarzschild coordinates, and then there's some geometry outside of the black hole horizon. But then you can change coordinates and do fancy things to extend the geometry in a smooth way past the horizon. And if you keep on doing that in the context of an ADS Schwarzschild black hole, you end up with some maximally extended space-time where, in fact, there are two asymptotic regions. And you have, from the point of view of either one of them, it looks like a Schwarzschild black hole. And then there's some space behind the horizon where potentially observers from both sides could meet. If this kind of diagram is not familiar to you, you should talk to me immediately after this lecture, and I'll be happy to go through, because people draw these all the time, and I think it's good to know what it means. So basically this basically indicates that there's this maximally extended geometry. Okay. Now, so CFT in a thermal state on a sphere. Well, does that describe this whole thing, or does it just describe what's outside the horizon, or does it describe something in between, maybe what's outside the horizon in these regions? So that wasn't really very clear initially. So back in, I think it was either 2001 or 2003, early 2000s, Juan wrote a paper where he clarified this issue. Okay, so he was specifically thinking about this maximally expanded geometry. And, well, he noticed, obviously, that there are two asymptotic regions. Okay. Or if you want, the asymptotic space-time is actually a sphere times a sphere. It's not just a single sphere. And by our basic rules of ADS CFT, that would suggest that the dual CFT should be something living on not just one sphere, but actually two spheres. Or equivalently, that there are two CFTs. Okay. And so he said, okay, well, if it's a state of two CFTs, what state of a pair of CFTs would naturally correspond to something like this, where each CFT looks like the thing dual to a black hole? Okay. And since I just talked about that, this might seem like a good choice. So this thermofield double is exactly a state where you have two copies of a system, and where each copy is in a thermal state. Okay, but the two systems are together in some particular pure state. Okay, so that's what Juan proposed. I'll write it down again, just. Okay. Okay. But this is so that sounds very plausible. But this is an incredibly dramatic statement. If you think about it, what it's saying is that you start with these two quantum systems. These have nothing to do with each other. Okay. it's one CFT, and then there's another identical CFT, and there's absolutely no interactions between these two things. Okay, it's like you have I don't know, a computer chip, and there's another one in Asia somewhere, and so there's no possible way that these two CFTs are talking to each other. You can't communicate between them, but you put them in this special entangled state. Okay, so you put them in this state. I mean, equivalently, you take a quantum superposition of these product states, and again, at each one of these product states. So what is this state dual to? If I have CFT in the vacuum times CFT in the vacuum, it's dual to two completely separate ADS spacetimes. Okay. If I have CFT in an excited state and the other CFT in a similar excited state, that's dual to two completely separate ADS spacetimes with some gravitational perturbations. Okay. But somehow by adding up all of these, equivalently by entangling the two systems, what you've, according to this proposal, done is described a space-time where these two asymptotic regions are actually connected by a completely classical geometry. So if I were to draw a spatial slice across there, okay, then what that looks like is you have some asymptotically ADS space-time, and then there's like a black hole, and then that opens up. Okay, so this is a geometry, basically a geometry that has a wormhole connecting to asymptotically ADS regions. Yes?
So, but here you have the same black hole, you just have to make the coordinate transformation, or you're talking about different systems?
Well, so when I was talking about different coordinates, what I meant was that there was a set of coordinates that conveniently describe the outside of the black hole horizon. Yeah. So this is a geometry independent of coordinates. There's this eternal ADS black hole geometry, which has two asymptotically ADS regions, and then this wormhole connecting it. And it looks like a black hole from the outside on either side. So that's the geometry that I'm talking about. And the proposal is that geometry, independent of what coordinates you use to describe it, is equivalent to that state. Yes? No. Yeah, it gives you, so the mutual information gives you S of A plus S of B minus S of A union B. This is 0 because the whole system is in a pure state, and this is 2 times the thermal entropy of the black hole. Okay, so there's a large mutual information, and there's a large entanglement entropy. And in particular, this is a case where the black hole entropy can be interpreted as entanglement entropy between these two CFTs. Okay, so if in this setup, the entropy of the black hole that before was just a thermal entropy of one CFT, it's equal to the entanglement entropy between the CFTs. And okay, and in this picture here, I'll draw it even clearer. Okay, so in this particular picture, okay, so we said the area was the area of this black hole horizon, but we can give it another interpretation of what that surface is. This black hole horizon, it's really, in this spatial picture, it's just this surface. It's like the minimal area surface that divides the two asymptotic regions. It's a minimal area surface where the one asymptotic region is on one side and the other asymptotic region is on the other side. Okay, so this is the area of the extremal surface. In this case, it's a minimal area surface separating asymptotic regions. Yes.
So when you give me this state,
Yeah.
I'm thinking particular time slice, or
Well, I normally think about these things in a Heisenberg picture, but so the CFT comes equipped with a Hamiltonian. Yeah, so there is a Hamiltonian that we know about here, and yeah, so I'm imagining this.
because the thing that's confusing me is like depending on which slice you pick, like if you pick the one center, there's the one.
Yeah, I mean, so right, so we need to be able to know how to do calculations at different times here. I mean, there's various things you could say about this state. So one of the things you'll often notice is that it's invariant under multiplying by h, right, t. So it's invariant under multiplying by this operator, and that's interpreted as the fact that it's the spatial geometry of that slice looks the same. Okay. Good. Okay. So, as a really quick aside, since we talked a bunch about the fact that there are lots of different purifications. Okay. So this is just one way to purify a thermal state of a CFT. There's all kinds of other purifications that you could imagine, either with just one other CFT, with another copy. Even with that same system, there's lots of other purifications. Or you could imagine other systems. And so, it's interesting to ask, well, what are those dual to? Okay. Okay. So what we expect is that the state of the one CFT is not changing. We're just changing the state of this auxiliary system that we're tacking on. And the minimal thing that we thought when we said that the CFT in the thermal state was dual to the black hole, the minimal thing we could have imagined would be that it was dual to the outside of the horizon. Okay. So if these other purifications are dual to something, we kind of expect that they should be dual to something that looks like a black hole outside the horizon. But maybe there's something different. Maybe there's other ways of extending this space-time past the horizon. Okay. In fact, there are other ways of doing that. For example, if you started with that space-time and someone sent in some energy that goes over here, or there was some energy that came out of the horizon. So there's actually lots of ways that you can imagine extending that black hole geometry past the horizon. That one over there is just the most symmetric and natural, but there's lots of possible geometries here, and so this would be the natural guess for what these other purifications would be dual to.
They all involve other excitations besides just the pure black hole geometry.
Yeah, so behind the horizon, there'd be other stuff. And we're going to talk more about this.
But not outside the horizon?
Yeah, so outside, because we have the same state of that first CFT.
You're on the left here.
We're on the left. We're on the left. Yes. Okay. Okay. Okay, so this example motivates pretty well this more general thing that Ryu and Takenagi said, although I don't think it was the thing that motivated them specifically. But let me go back to so now let's go back to a single CFT. Okay. So we spent half the lecture talking about how if I just have a quantum system and then I look at a subsystem, okay, well, a lot of the things that you would say about a subsystem like that would be similar to things that we said about, say, one of these CFTs. Okay, so that subsystem here, So let's. This is supposed to be. Okay, so this is the CFT picture. This is going to be time. This is a spatial slice. Okay, and we consider some subset A of the spatial slice. Okay, and so we've understood earlier that this subset should be in described by some kind of ensemble. Okay, and the complementary subset is going to be described by some kind of ensemble, and there's going to be some entanglement between the two systems. And so actually the structure is very similar to this structure that we talked about here in the thermofield double. Okay, in fact, very formal quantum field theory people often consider these field theories on these subsystems as really independent theories. So if you define, I'm going to define this subset of space-time, dA. Okay, so this is called the domain of dependence of the spatial region A. Sometimes it's called a whole bunch of things in the literature. Sometimes it's called the causal development of A. Sometimes it's called the causal diamond. Associated with A. And what it is all the points P such that any time-like curve through P goes through A. Okay, so basically, if there's a point P in that region, then there's no time-like curve that avoids that going the path that avoids that region. Okay, so it's basically just the stuff in the causal future of A and the causal past of A. Okay, in quantum field theory, so any operator which is localized somewhere in dA is determined by the density, so by the density matrix of the field theory for that subsystem. Okay. So assuming I know the Hamiltonian. So for example, if I have a local operator here, I could actually so psi of x and t. So I could actually, using the Hamiltonian, in principle, I could rewrite that as some kind of non-local operator living at this original time slice, which would be localized in the region A. Okay. So the reason I'm saying all this is that these domains of dependence regions. So when I have a subsystem A and its domain of dependence, the state of the field theory on A and the full set of observables localized within A, within this domain of dependence, in a sense, you can think of that as being a complete theory. Okay, so some algebraic quantum field theorists sometimes think of that as being a self-contained theory in its own right. And in fact, when we talk about conformal field theories, later we'll talk about an example where A is a ball. But actually, after a conformal transformation, you can map the domain of dependence of that ball to, okay, so that region maps to hyperbolic space times time, or actually alternatively, I think, to de Sitter space. Okay, so you can actually see, if I look at that region, which just seems like a subsystem of some field theory on Minkowski space, in an alternative picture after this conformal transformation, it's actually like an entire CFT on de Sitter space or on hyperbolic space. Okay, so there's a sense in which when we talk about a quantum field theory, and I break it into two subsystems, A and A bar, that I can really formally think of those A and A bar as being sort of two separate field theories. Okay. And so because of that, it's really not that different than this picture here, except that there are some interactions on the boundary. There's some local interactions between the two, but but for a lot of purposes, it doesn't matter.
Just about time, by the way.
Oh, okay.
Around the 2 o'clock.
Good. Okay. All right. Well, I'm just about done. Good. Okay. So if we have the full state of, say, our quantum field theory on I'll call it A and its complement, we can think of that as an entangled state of the quantum field theory on this dA and the quantum field theory on dA bar. Okay, and formally speaking, according to our general formula, that would look like, using this Schmidt decomposition, that would look like this. Okay. And now we can think of this in the context of ADS CFT. Okay. So let me think about, I'll just draw this picture. This is A bar, so my field theory is living on this space, which I'm representing as a circle. And then there's some interior, then there's some, well, that's dual to some geometry whose boundary is this circle. Okay. Okay. And so over here, we had a statement that the entanglement entropy, which is a thing that characterizes this entanglement between, it's sort of the nicest single quantity that's characterizing the entanglement between the two theories. What we said was, well, that corresponded in this dual geometry. What we did was we found a surface that neatly divided the space into two, such that it had an extremal area, and such that one asymptotic region was on one side and the other asymptotic region was on the other side. Okay. So Ryu Takenagi is the same statement over here. So here we've got our two theories are the quantum field theory on this region and the quantum field theory on this region. And we say, OK, well, let's find a surface in the bulk that divides our space in two somehow so that the one asymptotic region is on one side and the other asymptotic region is on the other side. And such that, out of all the surfaces, possible surfaces there, that this has the extremal area. And so Ryu Takenagi says that, well, you just use the same formula over there, that this extremal area over 4g Newton is what we're going to say is the gravitational interpretation of this entanglement entropy pi log pi. Okay. So it's in a sense it's quite natural. I mean, I think when it seemed very different from the black hole thermodynamics story when people first started talking about it, but I think it's extremely natural to make that identification. And I think the thing that struck me the most about this as an element in the ADS CFT dictionary, compared to all of the other things that people talk about, is that this entanglement entropy is something that we can really talk about for any theory. It's kind of a universal object in quantum systems. So it doesn't matter if I'm talking about an M5 brane or n equals 4 super Yang-Mills theory or some 1 plus 1 dimensional CFT. I can look at subsystems and I can talk about their entanglement with the rest of the system. It doesn't matter exactly what the field content of the theory is. And it's very beautiful that that kind of universal quantity on the field theory should be associated with something which, again, is universal among gravitational theories. So when we talk about gravitational theories that have a classical limit, the thing that you always have would be geometry. You could have other fields, gauge fields and scalar fields and branes and all kinds of things, strings, but this is something that's quite universal in the classical limit, and so it's quite nice that these two things are corresponding to each other. Okay, and that suggests the fact that it's so universal suggests that if there are universal things, other universal things in theories of gravity that you might hope to learn about, you might learn about by exploring this connection further. Okay, so that's where we're going in the next few lectures. Questions? Yeah, you and then you. Yeah.
So on this board, if I have a one-sided black hole that forms from collapse or something,
yeah.
As an entanglement entropy?
Well, so yeah, that's a good question. I mean, if of course there are, and we'll talk more about this, but of course there are pure states of single CFTs. When we talk about this ensemble. Well, yeah. So when we talk about this ensemble, okay, right. So we have various things that we can talk about. There's this thermofield double state that we've now seen to plausibly be associated with this fully extended geometry. I kind of argued that the density matrix itself, the thermal state itself, in a sense, carries the information about what's outside the horizon. But there was still some entanglement entropy that we calculate there, and that corresponded to the horizon area. But when talking about black holes, the other thing that people talk about would be just these microstates. So say I have, you talked about a black hole formed from collapse. Another thing we could talk about would be an energy eigenstate, which would be more time independent. But in either case, you could be imagining that we're talking about a pure state of a single CFT. But typical states in one of these thermodynamic ensembles should, if you explore them with any simple observable, give you the same answer as in the ensemble. And so if we do various calculations to try to understand what is the geometry dual to this pure state, at least talking about quantities outside the horizon, we're going to get the same answers. Okay, so all of the typical states in this ensemble should really look like this black hole outside the horizon. But then if you look at the entropy, the actual full entanglement entropy of the whole thing, it's just 0. And so then it's a bit of a puzzle. So if it's 0, does that mean that there's no horizon? Is the horizon singular? Is there a firewall there? It gets into a lot of interesting issues. So there's various possibilities. So one possibility is, hey, there's no entanglement entropy, so the area is actually 0. So therefore, as soon as you hit the horizon, you hit a singularity, and the bulk and the metric actually gives you something which could be interpreted as having 0 area. Another possibility that people have talked about is that, if in that case, if you want to understand the horizon area and what it's dual to, well, then you have to think about somewhat different concepts of entropy. So maybe there's some coarse-grained type entropy that is really the thing you should be thinking about. I mean, it's true in basic thermodynamics as well. If I have a gas in a box with energy of 1,000 joules, and it's in a pure quantum state, well, its entropy is 0. But is that really its entropy? You don't really. That gives a misleading picture of how much entropy the system has. And what you normally think of is doing some kind of coarse graining. And so one of the interesting statements in complicated systems like this field theory, even though the full entropy of that pure state is 0, if I look at so let's say I have the thermal state, and now I have some energy eigenstate, which is a typical state in that thermal ensemble. Okay, so it turns out that if I look at any subsystem which is not too large, okay, so and I think by too large it would have to involve half or more of the degrees of freedom. Then even though this one is pure and this one is thermal, the entanglement entropies for those two subsystems are going to be the same. So entropies for as soon as I start looking at subsystems, I'm not actually going to be able to tell whether I'm in the thermal ensemble or whether I'm in a pure state. Okay, so any kind of measure of entropy that had to do with coarse graining or looking at subsystems is going to give you the same answer. And so, a plausible answer would be that the area of the black hole horizon maybe should be associated with one of these more, somewhat more coarse-grained things.
You should probably let people get their coffee.
Okay, yeah. Sure.
So are you a basketball player? Those are rather impressive leaps.
Oh, yeah, well, a little bit. I used to be. So when I was 21, I could dunk a volleyball.
Oh, that's pretty. Oh, wow.
So
That's fantastic because you're no taller than me. And I could get a hand over the room, but I didn't have the coordination to dunk it.
yeah, I had to grab it.
That's impressive. Well, you.
Well, that's probably not.
Yes, I probably couldn't even reach the upper board now. There was a time. I'm not going to try.
Yeah. Yeah.